All right, here is your warm-up for the day. So go ahead. It should be very similar to what we did on Friday. You've got a scenario. You've got a toolbox full of data structures and ADTs. You pick the ADT and the data structure to implement it, and then tell me why. You'll see that the Slido, which might not be active yet, I have to click a thing, I think. I want to know what you picked. So did you pick an array list, a linked stack, an array queue, whatever is your fancy, and then give us a brief explanation as to why, and we will discuss in like 4 minutes. I'm going to make the Slido live. Go ahead, discuss. All right, we're going to look at the answers in like 30 seconds. So wrap up those final conversations. Nice. Is this the right lecture? Not this one. Okay, hang on. I'm going to do a thing. Ooh, I see some like last minute votes coming in. Y'all can see it live, right? I clicked that link list. I'm learning. It's happening. I thought it was fun for y'all to be able to see what other folks said. Though we don't get the combo of vote and feedback, unfortunately, in this version of the Slido. Okay, let's take a peek. Interesting. So I see linked stack, linked queue. I see a lot of linked queues, perhaps. Interesting, I guess, because I didn't press present. We're all stealing Casey's answer, which is also technically the answer of how it's implemented, so I stole it too. So you know what? Great minds, right? But like I said, there really is no technically correct answer to these types of things. I do think this sort of queue structure, because that's maintaining the order. So queue makes sense in this type of ADT. You could argue with me for list. It would probably be a pretty hard argument for stack in this situation. If we are sending stuff to the printer, how annoyed would you be if the person sitting next to you just kept interrupting your print job because they submitted their thing afterwards, right? So it feels like queue is probably the correct ADT. But then once we dive into those types of data structures, if you remember, we did talk about how like we have a bias towards the array because of some stuff that happens in the hardware. But you'll notice in this one of the simplest implementations code-wise, as long as we just sort of, treat it like a linked list. It's a pretty nice, easy implementation. That is actually how it is implemented in a lot of operating systems, though not all of them. But does anyone have any sort of points they thought were interesting, or anybody want to argue against my linked queue? I love a debate. I love to be wrong, honestly. Any interesting points? Any interesting conversations y'all wanted to share from your discussions? No? We're all convinced, and we're ready to add the new thing that we'll be shouting at each other about into our toolbox. Yeah? Okay. So hang on, let me navigate over to the right. There we go. Okay, and I will actually present this time. There you go. And theoretically, you would have seen this and made choices for yourselves, but there you go. But we're starting to move away from at least just that sort of high-level ADT conversation. There is another ADT that I do expect you to be familiar with, but we are going to talk about it so many times in this class. I didn't go over it last week, but the slides are still there. It's the map or the dictionary. Remember, that's the one where it's a non-ordered collection of pairs. I promise we will revisit that ADT a ton. But It is now time for us to move into the next level of analysis. So previously I was asking you, like, how would you use it? Empathize with your customer. Think about how you would implement it. What's the runtime? What's maybe the memory usage? Now we are going to do a double click and we are going to go a level deeper on that runtime analysis. And we're going to spend all of this week just on the runtime analysis math part. Full disclosure, this week used to be 3 weeks of this course. And then I was like, maybe we shouldn't ask you to write proofs. So we just reduced it to 2 weeks. And then all the other professors were like, Casey, you still make them do like actual algebra on their exams? That's not nice. And I was like, whoa, just me? So I cut a whole nother week of it so that I don't have to ask you to do the tree method on your midterm. When we get to Friday, hopefully you'll be like, yeah, Casey, good choice. But I will say that we do have a lot of slides to sort of get through. I'm sorry if sometimes in lecture I'm kind of like running through topics. A lot of this stuff, I'm going to be talking to you about the things that I think are best learned when I set context. But it might not feel like you fully are able to do the things I'm asking you to do. That's what section's for. Like, go in and practice it, okay? So I'm sorry if I kind of click over things fast. I promise you'll get more practice time. Great. Also, so we are officially at week 2. The quarter is off and running. We now have office hours happening. Please check the office hours tab for the office hours calendar. Note that our office hours for this course can be in different locations, so don't just assume. Always check the calendar. I also have office hours that are both drop-in and schedulable. So you are welcome to talk to me about anything. I will absolutely help you debug your homework assignment. If you want to talk about resume or career, I don't know. Somebody was mean to you. I don't know. Let's chat. Whatever. But you can go to my one-on-one link and you can find time with me there. The stuff you really care about. So reminder, homework. I really need to get very precise on these names because I'm going to mix them up all the time. Okay, so you've got 2 types of things I ask you to do on a weekly basis in this course. One type is like write some program with your buddies. We call those the projects. I might occasionally call it homework. I'm sorry. That is right now you've got that sort of like CSE 123, 143 review type of thing going on. Hopefully we've been exploring setup. The TAs told me that we've been getting a lot of good questions on ed about setup, so I know y'all have started. If you haven't tried the setup, please try the setup. Maybe just go to office hours, hang out. But you just don't want to be on Wednesday like, oh, I know it's not as complex coding-wise, so I'll wait till Wednesday to do it, and then you realize you can't set stuff up. That's going to be a bad time. I will also tell you that, yes, you are submitting things via Gradescope, and Gradescope has these magical machines called servers, and they only give us so many. And so if all of you try to run the tests and submit your thing at, let's say, 11:50 on Wednesday, you might encounter a bit of slowdown, and I can't control that. So I trust you to do these things early enough that you don't get bit in the booty by the 11:50 rush to turn in the homework assignments, okay? I inevitably will get some very sad email at like 12:05 that says something about a hang, and we will deal with it, okay? But like, I'm saying it now, don't be that person, though I understand. The second thing we will ask you to do on a weekly basis, I'm going to refer to as the exercises. Those are sort of like the written stuff. They'll look a little bit more similar to exam-style questions. Historically, I would pick some of those and put them on the exam, but I decided that's just a waste of everyone's time. So we're only going to do sort of the design-style stuff on the actual exams when we get there. But you are going to use that exam stuff to show us that you're keeping up with the algorithms, keeping up with the techniques that we're asking you to learn. As a compromise, I am going to be doing hopefully at least one of those style of problems, or at least putting the answers to one of those style of problems in the lecture slides each day of lecture. So those exercises will be 4 problems. 3 of them will be covered in lecture, and then 1 of them will be something you have to kind of think through a little more detailed yourself. Those are technically individual assignments. But Casey, I saw somebody talking to their friend about it at Odegaard. Yeah, I know, okay? It's okay, all right? Just like, be cool about it, like discuss the things, learn the things, don't just copy each other's stuff. It's not fun for us when we're like clicking through and you can tell there's like a hasty, just like exact copy. But it's okay to chat through things with each other, but I do need an individual submission from everybody on that written exercise piece. The rhythm we're going to get in is on Mondays, we will release a new exercise, and the exercise from the previous week will be due. You didn't have an exercise last week, so today, exercise 0 will release. It'll be due a week from today. And we will generally be in the pattern of on Wednesdays, we will release, if there is a new programming assignment, some of the programming assignments will be 2 or 3 week timelines. So that won't be happening necessarily every week, but you will always have some coding to do. Any course administrative questions? Yes?
Does everyone in the group have to submit homework 0 or just one person?
I only need one copy of the programming stuff. And when you go onto Gradescope, there should be an option that's like, who did you work with? And just make sure you actually add those folks. If I get an email from somebody that's like, they left me off, then I have to like go check and make sure you did mean to do them. So just like check that you added everybody. That's what I care about. So your groups are determined by your submission form on Gradescope. And I just need one copy. Any other questions? I'm going to assume that was everyone's question then. Okay, great. So let's talk more about this thing called Big O. We talked about these things called complexity classes. That's this sort of grouping of how the runtime, i.e. like the number of instructions, not like the clock time or runtime per piece of code, grows in relation to the size of the input n. So if you remember, if we were, say, searching for something in a linked list, it takes some amount of time to search 10 items. It takes linearly more amount of time to search 10,000 items, so on and so forth. If you see, the second column in here is something called the Big O. The Big O is really the complexity class, but we're going to use this notation where we use an uppercase letter O and then parentheses. And in the parentheses, we're going to use a very specific sort of stripped down version of the complexity class. We're going to talk about what I mean by stripped down a little later. But technically, you've kind of been already using Big O. We're just going to get real formal with it from here on out. So why do we care about Big O? Really, Big O is just a way for you to, at a high level, compare pieces of code as far as their performance goes. Now, up until now, we've kind of been intentionally picking code that we know follows clear patterns, that we sort of can, through a gut check or a pattern recognition, start to recognize the complexity class they belong in. So the general patterns I kind of expect you to understand by now is like, hey, if there's no loops, like that code runs exactly the same if there's 10 items or 10,000 items, constant. And we write that with capital O, parentheses, the number 1. There's no factor of n in between the parentheses, constant. If there's like one loop and it goes n times, like it goes over the entire set of input, or it goes from the front of the linked list to the back of the linked list, or it goes over every item in the array list because maybe you deleted the thing at 0 and then you have to shift everything forward. One loop, linear time. If you take that loop and then you put a loop inside of that loop that also runs in n time, then you get quadratic. So at a very high level, no loops constant, one loop linear, nested loops quadratic. But now I'm going to ask you to actually get really specific mathematically. What if we have other code that's got a lot of those things going on, or different things, or how do we know which piece dominates what other piece when it comes to runtime? That's what we're going to be talking about this week. Yes, motivation, why? I did mention before the actual like stopwatch runtime can just vary so much based on the computer and maybe even what's happening on your computer, so on and so forth. I also had this grand idea that I would show you all of these actual runtime graphs, and I maybe just lost an hour of my life like running a bunch of timing tests for funsies and then totally forgot that it was 3 o'clock. But let's look at one of them, and I will tell you that I'm going to post these later. But here, for an example, is a bunch of runtimes where, and I'll actually maybe even show you the code real quick, because I'm going to post this code for you to play around with. There are ways for you to actually like start a timer. You just sort of count what time the clock is on your code right now, and then you like go do something, and then you count what time your clock is at afterwards, and the difference is like your stopwatch. So you could always sort of, impossible to see. Yes, absolutely, thank you. Let's try this. Hang on, I'm going to click the thing. Half on. That is, yeah, I will have to also change dark mode. You don't have to look at this code. What I will tell you is that I will post this code for actual humans to see at a later date. I apologize. But essentially, you press start on the stopwatch, you do some code, you press stop. And so this is a timing test of me adding a different amount of ends into an array list, a linked list, and an int tree and an int search tree. I'll explain the int tree to somebody if you're interested later. It's technically on the bottom there, but underneath the yellow line is the array int list. It's really fast to add things into an array int list. It runs in that sort of linear time, and I'm looking at a number of values you can see that are so large that it almost looks invisible. But you can see on the linked int list and the int search tree, the linked int list runs this sort of quadratic time. You can see it's got that nice swoop. And then the int search tree actually kind of ends up running in this sort of logarithmic time over time. But like, look at how weird and spiky these are. It's not like this nice, clean, sort of predictive thing, right? And that's because, while I was running this code, I was also typing on these slides. And also my computer was like moving stuff around between the caches. And also, I don't know, like maybe it was moving that array stuff around. Or somebody pinged me, or who knows. Like there's a bunch of reasons why that spiky stuff kind of pops in there that makes it really hard for us to get at what we're looking at. So when I talk about big O, we're sort of abstracting away that nitty-gritty, that spiky, and we're going to move our thoughts instead into a more sort of theoretical place so we can do a better comparison. But I just wanted to show you how there's a reason why the actual timings don't serve us so well. So here is our roadmap for at least today and tomorrow. We're going to add more things into it. So we got to start with some code, and we need to get from code to some type of mathematical function that relates the number of instructions to the size of the input. So we're going to use f of n to represent the number of instructions and n to represent the input to your code. So if we had a for loop like this one, you can see here, it runs from 0 to n, and inside of it, it does a couple things. So the runtime function for that ends up being 2n. For every iteration of that for loop, I do two kind of things. And 2n, we further abstract away to just say, that's in the linear complexity class. I'm going to dive into more about how we abstract away. But that's sort of the goal. That's the roadmap of where we're headed. This thing that we're doing here is referred to as asymptotic analysis, algorithmic analysis. And it's that combination of first modeling the code. So code modeling is when I go from your actual code to that f of n equals something. And then the asymptotic analysis is when I go from that f of n equals something to the actual big O complexity class. So I've got sort of two stages that I've got to go through in order to get that nice, clean, big O complexity class. Let's talk about code modeling first. So code modeling, the process of mathematically representing how many operations a piece of code will run in relation to the input size n. There's a bunch of rules for this, but like I just sort of discussed on that last one, an example is a for loop that runs n times. There's sort of two basic instructions inside the for loop. So for each iteration, it's kind of like there's two. So we multiply 2 by the time the for loop runs. So we get kind of like an overall of like 2 instructions per each input size n. What counts? So we're going to do this very annoyingly hand-wavy thing where I'm going to say we're going to generally count a basic instruction as one runtime unit, if you want to think of it as that. So anytime we do any math, we add something, we divide something, we multiply by something, anytime we take a number and we assign it into a space in memory, like we put something into a space in an array, we put something into a variable, that all kind of counts as one. Anytime we return, anytime we say return and then we put a number in there and it jumps back to somewhere, that counts as one. Anytime we sort of like ask for a value from memory, those of you who have ever experienced any sort of assembly coding, you can see this sort of generally is relating to the core assembly things that we're doing. Basic math, moving data from one place, accessing data in another place, copying data, or doing a jump, meaning jumping to a different part of your code. That's typically regulated in the CPU as an actual like sort of clock timer thing. It is not a precise science. This is not assembly. This is Java. But that's kind of how we get this idea of like, oh, there's like, these are where these basic counts of one come from. And then we sort of go through and we find all those basic counts of one, and then we look at the control structures. How many times do we do each of those basic counts? So for example, if I had, an array and I was filling it up, inside of a for loop, I would multiply that thing inside the for loop by how many times the for loop runs. So if I, was doing, again, our example, I had 2 accesses of the array and I was filling them up, maybe I count each of those as 1 each. It's like, hey, put this number in this place in the array. Nice, clean, basic instruction, but I'm going to do that n times. I multiply the number of times the loop iterates by how many things are happening inside the loop. This also applies to any other sort of method call. If I have a method call inside of a loop, and maybe that method call goes out and does something else. Maybe that method call calls contains and has to search over a linked list or something like that. We have to keep in mind the runtime of that method call, and then we multiply it by the loop it's inside. So we sort of figure out these basic ones, and then we think about the control structures. How many times are we repeating those instructions? So function calls, of course, matter. There's a lot of complex things that could be happening there. Conditionals, that's another place that we need to count. Remember, we might have an if statement like, hey, if I is in the set, which means I have to do a contains method in that if statement to determine if I'm even going to join it. I have to pay attention. Contains probably, count something, or it's like if, not in. I don't know, Those types of things. I have to count the amount of operations happening in that if statement structure. And then, of course, loops. I don't make the rules. I just tell you the rules, okay? So the rules are we don't count the basic instructions in the for loop header, but we do count them in a while loop header. If you want to debate me about it later, we can have a debate, and all I can tell you is I didn't pick that convention. I'm just telling you the convention, okay? But again, you're going to see we're going to wave away so many of these basic numbers that you're just kind of trying to get a general relationship out of it, and then we're going to surface out to that complexity class. So the very specific counts that you do don't matter. It matters that you get that basic idea of the relationship so you can abstract it eventually to the big O. Let me give you an actual example. Okay, here we go. We've got method 1. So let's see if my animations do it for me before I start drawing on it. So we've got some variables we declare up at the top. We've got some math going on inside of a while loop. We've got a return. And I always start sort of inside out. I always look for what are the most basic instructions I can just kind of put a 1 next to. So I count hey, setting sum to 0, that's like a 1. Setting I to 0, that's a 1. Comparing I less than n, I'm going to count that as 1. It's just one comparison. Then in here, I might count the I times 3 as 1, and then I kind of add it into sum. Maybe that's 2, and then I assign it into sum. Maybe that's 3. If you can see how I sort of added up those pieces to it. And then maybe that's 2. I plus 1, that counts as 1. And then assigning it into I, that counts as 2. And then again, the return is 1. So this is me just sort of counting up the basics. This is not at all how I have started to iterate over these things. But before I do that, any questions on how I got any of these numbers? So I want to argue for a different number. Yeah.
Quick question. Here, I equals I plus 1 is counted as 2 operations. Does that mean when we're coding, if we do I plus
good question, and actually a very salient reason as to why I wrote it exactly this way. So if you recall, I equals I plus 1 is the same as I plus plus. I plus plus is just a shortcut. It's just to make the code more readable for us. It doesn't change what's happening underneath. So technically, I plus plus, you could maybe argue counts as 2 in a way. Yes?
And is it a 2-unit line because we're accessing the variable and doing math? Is it assignment and math?
Yeah, assignment and math. Yes, absolutely. Yes.
Would you have to multiply like 6 for like the while loop by n?
Ooh, what an interesting segue question. So if we sort of think of 6, like I see where you got 6, we've got the 1 for the while loop, we've got the 3 and the 2. So we would count those as 6 total. And if we think about how while loops work, we're going to have to redo that comparison every time the while loop comes around. So we multiply those 6 items that are happening by how many times that while loop's going to run, and n happens to be in the while loop test because I'm trying to be nice to you in this first example. So we could kind of say this is a 6n sort of expense of runtime here for the total while loop. I counted the 6 for them individually, and then I multiplied it by how many times the while loop runs. Questions? Yes? Oh, what happens if, say, you have a situation where your while loop, maybe it runs a different amount of times within another loop? Like, let's say maybe you are sorting a list and it gets more and more sorted over time. So could it cause an exponential runtime? Yes, it could. Once upon a time, me and Casey used to make you do a bunch of summations, and you had to do that sort of algebra, but I'm not going to make you do it in this iteration of the course anymore. But yes, absolutely. It does matter, so you have to pay very close attention to the loop bounds. This is a pretty linear looking loop, but you can imagine there's different ways to sort of figure out how that while loop is going to run a different amount of times depending on the scenario. And I will show you examples, I promise. So I end up with a code model of this example of 6n plus 3, the 6n from the while loop and the 3 from like the other stuff that's kind of bumping around on the outside of it. Any questions? Yes? A great question. I love that you're looking at the specific because you're like, well, does that condition actually get run 6 or n times, or is it really going to get run like n times plus 1 times because we got to check it in order to exit the while loop, right? I think technically the answer is yes. Like if we had an n of 5, that I minus n would get run 6 times because it's got to run 5 times to pass and then the last 6 times to fail. But in the ever annoying Casey's promising you that I can just wipe this stuff away, that plus 1 just like doesn't matter. So we don't think of it that way. We think of it in this way because this makes our math kind of nice. Like, how many things are happening there times the while loop runs? Yes?
Just to clarify, for code modeling, we don't need to consider the method call itself?
Yes, we do not consider the method header because there's not really anything happening there other than people passing us parameters. Yes. Let's do another one. Okay, this has a bunch of stuff in it, so why don't y'all actually take a couple minutes and chat this through with each other because I think you're going to come up with a lot of great questions for me. So go ahead. Let's take like 4 minutes, discuss this. TAs, if you want to help, I'm sure there will be a lot more hands this time around. Take another minute. I'll tell you what I care the most about is the factor of n, not the specific numbers. Make sure you get to the right factor of n. right. Let's see what we got. You might disagree with what I have on this slide when it comes to the individual numbers. Like I said, we're trying to get a general sense of the individual numbers, but in a few slides, I'm going to tell you that coefficients don't matter. So, but it's fun to count through it. And also what I think is most important about this code modeling skill set is the ability to look at your code with this level of specificity. Has anyone ever asked you to look at your code and count? Like, how many instructions are you really telling the computer? That's the level of detail I need you to be considering when you're thinking about your code. So let's maybe start at the top. I think that's how my animations work. How many would we give the int sum equals 1? I agree. Yeah, 1. How many would we give that int I equals 0? 1. Cool. Okay. Now, how about just that test of the while loop? When I do that I less than n, how much are we going to count just that singular test? 1. I agree. Yeah. Okay, now we've got int j equals 0. Love it. Okay, we've got another while loop inside of this one. How much for that test? Oh, we see a pattern developing. Now we've got an if statement, which has its own sort of math and then comparison thing. What do we think for this one? I like the fingers. Yeah, 2. Let's see what Casey said. Yeah, okay, apparently I agree. 2. You could probably have put 1 there and I could have been convinced. But I'm getting the 2 from doing the math on j and then comparing it to the 0. That's what's happening there. Now, the thing here is, remember, it's always going to do that if statement check. It may or may not enter the if statement, but because I was trying to be nice to you, there's do nothing inside of the if statement, so it actually doesn't matter. But that is another piece that we are going to have to incur every single loop. We're always going to have to check the if statement. Whoops. Oh, okay. Whatever. I times 3, there's 1, plus j, that's 1, plus sum, that's 1, an assignment. I think I got to 4. That's how I got there. Yeah? And then how about the j plus 1 equals j? Cool, great. And then the I equals I plus 1? 2, yes, and then a return? Great. Does anyone have any questions on sort of that basic count of instructions? Now let's get into the part that I assume was where most of the debating happened. Again, I like to sort of work inside out. So I'm going to start with that sort of inner while loop. So let's see. According to this, I've got 1, 2, 4, and 2 happening. So what is that? 9. Great. And how many times is the while loop going to run? Aha, yes. It is going to run n times. Yeah? Yes, because this plus 2 is going to happen. If you notice, it's on the outside of the if statement, but on the inside of the while. So j is going to start to 0, and j is going to count up by 1 until it gets to n. So that's why this is going to run n times. What if I only incremented j inside of that if statement? How many times would this while loop run? Would it run more than n times or less than n times? I'm only updating it every other time. Stop. And with the odd stuff, it could do some weird things. We could get into an infinite loop situation where if we got into an odd, it would never update, insert all of that stuff. But if I wanted to say, like, kind of do this in a weird way, I could, like, be tricky and change that j to j plus 2 and then put it inside that if statement, and then it would run n times just to mess with you. So pay attention to those kinds of things. I try not to be tricky on exams. Okay, so now we've got a 9n plus some other stuff sort of collected around. So now it's time to think about this outer while loop. So I kind of think of that as 9n plus 4. But how many times is that outer while loop going to run? What's the overall of that one? I agree. That also runs n times. So we end up with 9n plus 4 times n plus the 3 that's kind of kicking around at the end. So this ends up being a n squared style of relationship here. We end up with a quadratic relationship, which makes sense. We've got nested loops. Questions? Practice will make this a lot clearer, I promise. And you will do lots of practice with the TAs, all that good stuff. Yes?
I was confused because I thought like you could just keep it all in one loop, so I never thought of the inner or I just thought it would be like 11.
Yes.
But we have to consider
The inner, yes. Because each time we enter the outer while loop, that inner one is still going to run n times. So it's like a super fast little wheel and this outer, like slower wheel, and we're caring about the combination of those two. So that is how we get to that quadratic, and why a nested loop almost always means quadratic unless you have some very clever loop bounds. Okay. So that's code modeling. That style of code model should apply to pretty much everything except recursion. We are going to spend all of Friday just talking about how to model and analyze recursive code, because we know recursive code is just so special, especially confusing. So we're going to do that on Friday. But this should apply to pretty much everything else, okay? So we've done the code modeling. Now it's time to do the asymptotic analysis piece of it. Now we've got this sort of fancy equation. How do we go from that to the big O? So the reason we care about complexity classes, I'm going to show you, is at scale, all of these constants, just kind of like when you graph them, it's like they just drop away. They don't matter so much. When I'm talking about billions of n, that little +3 hanging off the end just doesn't really impact the runtime a lot. So I'm trying to kind of group these functions' growth into these complexity classes for a quick and easy comparison. So what I do is maybe I factor it all out, and I see I've got n squared, 9n squared plus 3n plus 3. And so right away, I know what's going to happen is that n squared term is going to what we call dominate the other two terms. I know it's pretty aggro. And that's going to be the one that leads to the overall runtime. So it's like, yeah, there's a constant term. Yeah, there's a linear term. But the quadratic term is going to contribute to the growth so much more that I can just drop those away. And then it's a complexity class. So I really just care about that n squared. I don't care that it says 9. I could say 3. It could say 10. I don't really care. So I drop off all constants, all lower orders of n, and all coefficients. And I end up with n squared, and that's how I went from code to big O. More examples. So we've got 6n plus 3. I drop off the constant because the 3 plus 3 is really not going to impact the runtime of this a lot. And then I care about the class, so I don't really care about that coefficient. Everything that's linear kind of ends up looking linear in the long run. So 6n plus 3, I wave away those constants and those coefficients, and I get n. This is why when I was like, I don't really care about the specific numbers, what's important is that you think about things at that level, like you look at each line of code, and then you think about how your control structures impact the growth overall of those instructions. I'm going to show you some reasons as to why this works, the dominating term. So dominating terms, also, I'm not a good math person. If you're a really good math person, you probably know this better than me. But let's say we've got, n plus 10, and then we've got n squared plus n plus 10. If I graph that, that's what n plus 10 looks like, right? If I graph g, it looks like this. And so you'll see that the shape of the growth takes the higher order term. So the complexity classes we look at, we want to look at that overall shape of the graph, which is our sort of high-level comparison to the overall runtime. And that's why we are caring about these as they tend to infinity. We care about high, big numbers for this. And so we're going to pick the dominating term to be the complexity class this falls into. We don't really have time for this, but you can look at all of them, and there you've got some answers for you. Great, cool. Can we throw this all away? Here's another reason why we can throw away the coefficients. So we can throw away the lower order terms. We can also throw away the coefficients, because maybe this is a graph of n and like n plus 10 down here, but when we're graphing it out to 200, those things will just like look like they lay right on top of each other. So yeah, they're technically different, but again, we just care about such big numbers that those types of things just don't really impact the runtime we're talking about. Do I have one more in here? Okay, great, great. Yes, thank you. You can read all those things. And then here's the coefficients. Perfect. Okay, so now here's n and maybe here's 2n. Those have got to be different, right? Like those feel really different. Like one's twice as fast at growing in relation to the other. But again, at a much larger scale, those things just shrink in comparison. And so that's why we constantly just don't really care about the constants and the coefficients. We're just trying to sort of abstract those away to get to the overall complexity class, which means find the highest order term of n. So if you were doing this, if you said something, was like a +4 instead of a +5 or something, I don't care. But if you said something was an n dominating factor instead of an n squared, I care. Hopefully this is a little bit clearer as to why I like wave stuff away and all that good stuff. You're going to get more experience. Okay, great. Then, perfect. The one thing you should also know, here's more examples of it, is that we think of big O as tending to infinity. And what that means is that for something to be considered in a complexity class, there must be a point at which after that it lives in that complexity class. So we have this sort of concept of like n naught. And that's actually in the formal definition of big O. It's like if there is some singular point in time, some value of n, after which it grows in this way, we think about the one that grows to infinity. This actually does matter. A lot of the Java stuff will implement things for smaller values one way and for larger values a different way, just because of efficiency and stuff like that. So here is the formal definition of big O. Something is considered in the set of the big O complexity class you're talking about such that all values past some value of n naught satisfy this f of n is less than or equal to some constant c times that order of n. So as long as the only difference is a coefficient and there is some n naught after which it persists. The next page is the first problem for your exercise, and I will give you the answer to this really quick, and then I will post it because I don't want to be that mean to y'all. But here's a bunch of runtime graphs that maybe look a little weird to you. And so what I will say is the trick to these, show up. Oh, if I can draw. Is to draw fit lines around it. Don't get confused by these lines. If you can see here, there's sort of like a lower base, and then there's kind of an upper base, but look it, those are both linear. So what is the big O of this one? Exactly. Here's one that's really tricky. I'm going to kind of draw a fit line, like that's sort of the maximum value, and that's kind of the minimum value, and even though it varies in between those, it's flat. What is the complexity class of something that's flat? Exactly. O of 1. There you go. It's about how it changes over time in relation to n. I will post the actual cleaned up solutions to these so you can do it for your exercises. Thank you all so much for being here. Please feel free to ask your TAs lots of questions and get started on homework. Project 0.